Alright folks, so today we're going to be learning about bond energies. So hopefully when you think about breaking a chemical bond, you're thinking about the fact that you're going to need to put in a little bit of energy to make that happen. Sort of like if you want to break a stick, you're going to need to put a little bit of energy into it to break the stick into two pieces. So in chemistry there's a special name for the type of energy that you put in for that to break that bond. It's called bond dissociation energy. And so let's visualize that for a bit. So imagine that we have a simple diatomic molecule, although we could use more complex examples. I'm trying to provide a really simple, straightforward example here. If we add a little bit of energy into that, bond dissociation energy, then what we're going to do is we're going to be able to break that bond and have those atoms floating freely and separate. So, as with any type of, any form of energy, be it thermal, gravitational potential, etc., we're going to be looking at units of joules, or versions of that. So the kilojoule per mole is the unit that is used for bond dissociation energy. Okay, so it's indicated for a specific chemical quantity. Okay, so kilojoules per mole, meaning the amount of energy per mole of that substance. Okay, so for example, if in a particular molecule there's a bond between hydrogen and fluorine, and we want to break that bond, okay, we would have to put in 565 kilojoules for every mole of HF bonds. And what that would give us would be 1 mole of H atoms and 1 mole of F atoms floating freely. Okay, so luckily other scientists have done the hard work for us in measuring these values, and they're found in a table on page 307, 308 in your textbook. So if you need to stop this video and find that page, then go right ahead. What you should see is something that looks a little bit like this. I've just taken a portion of it, although it is a little bit larger in your textbook. So you'll see, for example, to break an HH bond requires that we input 432 kilojoules per mole of HH bonds. But we want to be careful when we are looking at a particular reactant or product molecule that we know the type of bond it is, whether it's a single bond, a double bond, or a triple bond. For example, over here, you can see that a carbon-carbon double bond will require 614 kilojoules of energy, whereas a carbon-carbon triple bond will require more energy. And that should make sense because breaking a triple bond should take more energy than breaking a double bond. Okay, and I would guess that, although it's not on this particular chart, that a single bond between two carbon atoms would have an even lower bond dissociation energy than what we're seeing on this chart. Okay, so we can use bond energies to calculate our enthalpy of reaction, or delta H. And so this is just an alternate to using our standard enthalpies of formation that we've been using. This is just another method that will allow us to accomplish a similar task. So it turns out that the enthalpy of a reaction can be calculated if we take up all of the bond energies of all the reactant molecules and we subtract all the bond energies of those product molecules. So I'm going to take you through an activity, a question that will help you practice doing that. Okay, so here's the example. So if we say use bond dissociation energies to calculate the enthalpy change for the following reaction. So in this case I have some hydrogen gas and fluorine gas reacting to make hydrogen fluoride. So the first thing I always want to do is I want to write out a balanced chemical reaction equation if it's not given, but in this case it is. So the next thing I want to do is make sure that I take a really good look at what the structure is of the reactant products. And mainly that's because I need to know what atoms are bonded to each other, because even if they're in the same molecule, they may not be in a bond. And the next thing I need to know is I need to know whether it's a single, double, or triple bond, because as we saw before, the values for bond dissociation energies change dramatically depending on the type of bond. So without drawing a Lewis structure, it's really hard to tell these things. So our second step is going to be to do exactly that. So I've done that. So I've got my HH bond there. I'm making sure that all of my atoms have the required number of electrons to make sure that they're stable. And because in my balanced chemical equations I see that I have two quantities of HF. Now I could write a little 2 beside here and remember that I have two HF bonds, but because this is a simple example and it's our first one, what I'm going to do is I'm just going to draw it out. So we can see in fact that we have two HF bonds, and that needs to be taken into account when we're doing our calculations. So the next thing that of course I want to do is to start to fill in that formula that we just saw, the next thing to do is to figure out the sum of the bond dissociation energies for all of my reactants. So that's these guys over here. So I'm going to go about doing that. And so it turns out that if I look at my table, I can see that an HH bond will require 432 kilojoules per mole. And since the coefficient in my balanced chemical equation is 1, that means that on the reactant side I only have one HH bond in total. Okay, then I'm going to do the same thing for fluorine. And fluorine, when I look up the value for its bond dissociation energy, it is 154 kilojoules per mole. So there I go. And when I add those up, the grand total is 586 kilojoules per mole. Okay, now what should I be doing next? Well, I should be doing the same thing for my products. So the difference here, though, is that I have one HF bond, but I have 2 moles of HF. So I need to take that into account and multiply the bond dissociation energy for HF by 2. So just check that value on the table to make sure that you know where it's coming from. And so when I do that calculation, then I see that the grand total is 1130 kilojoules per mole of energy that needs to be input in order to break apart my products. Okay, so now I'm going to put those two quantities, the bond dissociation energy for my reactants and my products, into that original formula and subtract them. So that total enthalpy for this reaction is going to be the bond dissociation energy of my reactants minus the bond dissociation energy of my products. And so filling in the values that I got in earlier steps 3 and 4, I end up with a final value of negative 544 kilojoules per mole, which tells me that this reaction is exothermic because of the negative result that I get. Okay, next we're going to move on to a more complicated question.